Okay, good afternoon, everyone. How are you all doing today? Are you ready for the weekend? Looks like somebody's weekend already started. Oh, all right. Let's continue with our topic. Before the class, there were a couple of questions, and so I'm just going to take a few minutes at the very top of this class to answer those questions. Um, Here, question was about these symbols. All right. So okay. So here we talked about the diode, and this is the standard symbol for a diode, right? The arrowhead with a perpendicular or horizontal line running across the tip of the arrow. So that's the standard symbol for a diode. If we have arrows pointing out from this diode, it indicates that it's emitting light. Hence, we have an LED, a light emitting diode. LEDs become a very ubiquitous term in modern day lives. So that's what it stands for, light emitting diodes. If there is light that falls onto a diode, like this, then it's receiving, or light is incident upon the diode, and then that's a photodiode. Okay, that's known as a photodiode. Which is what all solar cells are. You have light energy falling on top of a solar cell. So you have photons coming in, impacting. Those photons impart energy to the semiconductor material. A small portion of that energy, or the photon energy, is transferred to the electrons. The electrons acquire sufficient energy to break their bonds and start flowing to the circuit. That's the basic operation of a solar cell. Then we have this kind of diode. This is known as a Schottky diode, named after the person who invented it. A Schottky diode is a very high-speed diode. It's made from the contact of a semiconductor material and a metal contact. Okay, so it's a Schottky diode. Another far more common diode has whiskers on its cathode, and this is known as a Zener diode. And the Zener diode is operated specifically in the reverse bias, or in the reverse mode of operation. So those are just, at this point, all of this information is kind of, I want to say, we are not going to do technical studies on these devices until much later. Okay. For now, this is simply an introduction of what these devices are and what they can do. Right. So each one of these has a specific purpose. Diodes, by the way, there's an excellent question asked. Can it conduct current in both directions? So if we take a look at this vacuum tube diode, the operating principle of this vacuum tube diode was that the cathode is heated up, and the thermal energy that is acquired by the electrons allows them to um, move in response to an externally applied voltage. But if you reverse it, the anode doesn't have a heater filament. And because the anode doesn't have a heater filament, it only conducts current in one direction. Electron flow is only from the cathode to the anode. And that's it. Which is exactly the purpose of this device. We want current conduction only in one direction. We want it to be a one-way street. We do not want it conducting in both ways or both directions. So diode, and as I said, this question was excellent. Diode conducts only in one direction. It's a one-way device. Okay, diode is a one-way device. The semiconductor diodes, all of them are also one-way devices. If we do connect a reverse, or if we work them in the opposite direction, meaning we flip the source voltage, then we say that it's operating in the reverse mode or reverse bias. So the reverse mode, nothing will happen. There's no current that is flowing through. So it behaves as if it's like an open circuit. There is no pathway for conduction. Now, as with all things in life, every system has a breaking point. So the diodes also have a breaking point. As the voltage or the energy that is applied to the diode increases, it'll resist up to a certain point. That point, depending on the design, could be up to 50 volts, 100 volts, 200, 300, even 400 volts. There are power diodes that can function at thousands of volts. Okay. So if you take a normal diode, which I believe you have the 1N4000 series or 1N4148, which ones do you have in your lab kit? Did it have like a black epoxy packaging? Anyone know? Okay. All right. So if they have the regular diodes, depending on the numbers, 4001, 2, 3, 4, 5, 6, 7, 4001 can go up to 50 volts in reverse, whereas the 4007 can go up to 400 volts in reverse. You could technically take that 4007, stick it into a power outlet, and nothing will happen to it. It'll just behave like an open circuit. Okay, so those are some questions about the diodes. Let's take a pause. Let me know if you have any questions. So a question being asked is the one-way device, is it going from cathode to anode or anode to cathode? Another excellent question. It goes, so the electrons, specifically for this vacuum tube, are going from cathode to anode, but the current flows from anode to cathode. So again, thank you for asking that question. The clarification is the current always goes from anode to cathode. Yes. So question being asked is, what are the applications for a diode? The most important and the most common application for a diode is in rectifier circuits, where we use them to convert AC to DC. So every single device that we are using, and I believe I mentioned this before, all of the consumer electronic devices like this writing tablet, this monitor, the projector, smartphones, tablets, laptops, everything runs on DC. Okay, everything runs on DC. If it's a portable device, it has its own battery, either inside or external to it. And then we charge that battery, frequently. So the charging that appears at the end of your adapter is DC, yet we plug it into our power outlets, which is AC. So our adapters do the job of converting AC power outlet voltages into DC. And a diode's most common and the most important application is in rectification, because it's in one direction. You have AC, which moves in both directions, right? And you feed that into a diode, it'll only allow current to flow in one direction, doesn't allow in the other direction. That's the absolute first step in any rectifier circuit, in any adapter, any charger. Diodes are at the front end. We convert that AC into bidirectional AC is converted to a single direction AC. And then there are other applications like clipper circuits, clamper circuits, Zener diode regulators. All of those you will study in 315, 315. All right, good questions all. Hey. So to answer that earlier question, just expand on it a little bit more. Current is opposite of the flow of electrons. So electrons are flowing in this direction, and the current I is flowing in the opposite direction. So again, electrons and current I. So if we combine it with a symbol of a diode, the triangle needs a little work. Diode voltage, so this is the anode, this is the cathode. Diode voltage VD is always measured with positive at the anode and negative at the cathode. And ID always flows in this direction, from the anode towards the cathode. Those are the reference direction. Okay, those are the reference directions and the polarity for the diode voltage and the diode current. Let me put a box around it. Okay, always goes from anode to cathode. So unlike a resistor, unlike a capacitor, unlike an inductor, a diode and other electronic semiconductor devices, they have specific voltage polarities and current flow directions. All right. So speaking of capacitors and inductors, let's give it a few more seconds while everyone finishes writing down. Okay. All right. Speaking of capacitors and inductors, we introduced the topic. We looked at the equations, logarithmic. Symbol for an inductor is shown right here. It's a spiral coil. I'm assuming everybody has taken the physics classes where you've studied inductors, right? Inductors and capacitors, at least some fundamentals. So every electrical wire or any wire by its very inherent nature has some resistance, it has some inductance, and it has some capacitance. Okay? There is no ideal component in real life. So theoretically, when we draw a wire, we say that this wire has a resistance of 0 ohms. But that's not true for a real version. This is an ideal wire or ideal conductor. A real life wire or a real life conductor or a real life cable inherently has resistance, it has inductance, and it has capacitance. It is just too small for us to, I wouldn't say measure, but it's too small to interfere with its operation. As an example, if you take 100-foot or 100 feet long extension cable, like a power extension cable, and you plug it into your wall outlet, if you have 120 volts at your power outlet, that 120 volts might drop to, let's say 119 volts 100 feet away, perhaps. I'm just saying there might be some resistance in that cable. So even if that voltage drops, because of the resistance of that extension cable, that resistance is not in such a large number as to affect the fundamental operation of that cable. Does that make sense? Right? The resistance is present, but it does not interfere with its operation. Then it has inductance and it has capacitance. And again, that inductance and the capacitance also does not affect its operation. If you expect to run an appliance at the end of the 100-foot cable, it'll still work. Now, in some cases or other cases, we do have to worry about it, especially if it's like wired communication signals, which are like small voltage, small current. Like, let's say a USB cable, for instance, or an HDMI cable. If I plug in a 100-foot long USB cable into the computer here, and I try to run something 100 feet away, chances are it may or may not work properly. Because a USB cable, the data signal is probably, just a few volts or less. Power line for a USB is 5 volts. So depending on the resistance of that 100-foot USB cable, our data might not transmit properly. Then the resistance and the inductance and or the capacitance of the cable might interfere with our signal. There's just some practical considerations to keep in mind. Okay. Now, coming back to our inductance. So a wire has resistance, it has some inductance, it has some capacitance. Typically, we do not worry about it. This is an ideal wire. However, in real life, if we wanted to, if we take this wire and we transmit a current through it, a magnetic field is going to surround that cable or that wire. And magnetic field is very, very weak. However, if we take that same wire, current carrying conductor, and we wind it up into a loop like this, so a current carrying conductor or a current carrying wire, if you wind it up in a loop, that magnetic field gets a little bit stronger. And if you wind it up into multiple loops, you're now establishing a magnetic field through that conductor. The magnetic flux lines go into and out of that spiral coil. So that's the magnetic field that is established. And this magnetic field can store energy and it can release energy upon need back into the circuit. And we call this as an inductor. The symbol for an inductor is shown here. It is noted, the notation for an inductor is L, because I is reserved for current. So inductor is noted as uppercase L. Lowercase l is length, uppercase L is inductor in electrical engineering. And the unit is named after a researcher called Henry. Or H for short. Typical inductors are very small, typically on the order of millihenry or even microhenry. Okay, millihenry or microhenry. Typical inductors are very, very small. All right, let's take a pause, think over that. Let me know if you have any questions. Okay. So voltage, anytime current flows through an inductor, voltage is established across the terminals. That voltage is directly proportional to the rate of flow of, or the rate of change of that current. Anytime the input current changes, the voltage would change. The property of the magnetic field is to establish a voltage that is opposite of the polarity of the incoming current. And so it opposes any change in the input current. That is the property of an inductor. Mathematically, we state V is directly proportional to di over dt. Proportionality constant is L, inductance L. So the equation for the voltage is V equals L di over dt. The current is the same, except we now integrate both sides. So if you integrate both sides, what do we get? Again, I is equal to 1 over L integral V. So if we wish to find the voltage for an inductor, we take the time rate derivative of the current. And if you wish to find the voltage from the current, sorry, if you wish to find current from the voltage, we integrate the voltage over a certain time period, so 0 to t. Okay. And the other things I think we already talked about, the subscript L simply stands for inductor. If you have multiple inductors in the circuit, we would have VL1, VL2, VL3. If you had just one inductor and one capacitor in the circuit, you would identify it as VL and VC. If you just had the inductor and nothing else in the circuit, we might just call it V. Right? So that's just a notation. The subscript is simply to note which component we are referring to. And then of t, which is this, is simply meaning it's a function of time. Okay, it's a function of time. All of these notations are valid. So you might encounter any of these three kinds of notations in in engineering texts or anywhere. Okay. All right. Okay. Capacitor. Capacitor is nothing but two parallel plates separated by an insulating material. And hence the symbol for a capacitor is two parallel lines separated by a small distance. That's a capacitor. Symbol is shown right here. Notation is uppercase C. Unit is named after Michael Faraday. And it is known as a farad. Or uppercase F. Typically, these are on the order of microfarads, nanofarads, or even picofarads. Okay. Typically, they're very, very small and tiny. So capacitor is nothing but two parallel plates, two conducting parallel plates. Let's put it that way. Two conductors separated by an insulator. If you put the two palms of your hands together, they're separated by air. And so we can say I have a capacitance between the two palms. Okay. Capacitance will be very, 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 very small, but it'll still be present. If you have two conducting plates separated by an insulating material, between those plates, you have capacitance. But the capacitance needs two plates. So you have two rectangular plates running across each other. Then the capacitance appears only in the overlap section. Right? So if you have two plates running like this, the overlap is only here. And so capacitance C is only in that spot. It needs two plates, not one. So these are two overlapping plates. And the property of a capacitor is that it creates an electric field or electrostatic field and then energy is stored in that electric field. Okay, so like an inductor, the capacitor stores energy and then releases it back into the circuit at a later point in time. Inductors and capacitors are very similar, but they're also duals of each other. Okay, they are exactly the same in many ways and exactly the opposite in many ways. When we do AC analysis, you will see how the voltage and current for each inductors and capacitors relate to each other. Okay, there are real life applications that we use. One of the most common ones for an inductor is to use as a ignition coil for a vehicle. You've heard, right? Ignition coil, my starter ignition coil went out, and so it used to be an ignition coil. So it would store charge from a battery. When you turn on the ignition, you're releasing all of that stored energy all at once. And so all of that stored energy released all at once allows to start the engine. Yes. So question being asked is, when do we tell the elements to release the energy? So it could be it's depending on the input to the system. So for instance, let's take a real life example. Capacitors are used in camera flash, right? Camera flash. Nowadays, you may or may not have seen, like, professional photographers use those flash modules that are mounted on top of their cameras, right? If you've ever paid attention, sometimes you might have heard a whining or a whirring noise where it's and it starts it. That is the capacitor being charged up from the battery. When the shutter is pressed, it sends a signal to the flash module to release all of that energy all at once. And so the capacitor has stored the energy. There is no pathway for the capacitor to release the energy yet. Again, if you remove, so you send energy to the capacitor, capacitor stores the energy. If you remove any connection to that capacitor, meaning there is no pathway for the energy to discharge, then nothing will happen. It will keep that energy stored. When the shutter button is pressed, pathway flows through, signal is sent, and the capacitor releases all that energy all at once to the light bulb, and then we see a flash. Hence, the name of that module or the name of the device is known as a flash. So to answer to your question is depending on the application, on how long we want to keep it. Yes. That's also another good question. So why can't we just have a light bulb just turn on? Because it would just drain the battery in a matter of, well, depending on the size of it, in a matter of minutes, perhaps, maybe an hour or so, all of that battery would be drained. So right now we have these LED lights running, right? They have a constant power source. But if I was to connect a simple LED to another battery, depending on how much energy the LED uses, well, it's just going to keep the lights on for a while, but then eventually it's going to die out. So we don't just keep it on at the same time. Is that your question? Why don't we just keep the light on? So if I try to understand the question, let's see. Why do we use the capacitor? Why not just have the battery? Oh, one of the things is that the capacitor would be able to provide a large amount of energy in a very short period of time. So the battery is supplying some energy to the capacitor, right? It keeps supplying this energy. The battery is not able to release all of its energy at once. If it releases all of its energy at once, then it gets really hot. And so the battery is going to cause thermal and heating effects. So we don't want that. But if you want to release a large, powerful flash of light just for a microsecond where we are taking the picture, then yes, we store it all in the capacitor and then it releases all of that huge energy all at once. Yes. That's another good question. So if there are electrons, if it's separated, how is current flowing, or how is our electrons moving in there? The answer is they are not. That is an excellent question. So they don't flow. And that brings us to the answer to this question. So if we apply, let's say, let's take a simple battery. This symbol represents a DC battery. Okay, we have voltage sources, right? We have a circle and a plus minus. But this symbol right here represents a DC battery. Sometimes some authors might use it for AC also, but it technically is just a battery, and a battery is just DC. So the longer line is the positive end, the smaller line is the negative end. So if we connect this to a capacitor, the answer is that there are no electrons that are actually flowing through the capacitor itself. The reason this works is because there are these two metallic plates in the capacitor, and these metallic plates, they have electrons. These electrons in the wire and the plate get attracted by the positive terminal of the battery, so they start moving in a counterclockwise direction. On the other side, the electrons are repelled by the negative terminal of the battery, and so we have an accumulation of negative charges here. Actually, let's not do it this way. We have an accumulation of negative charges here and an accumulation of positive charges here. Because electrons have moved away, when an electron leaves, the nucleus of that atom stays in place, right? Only electrons are free to leave. So electrons leave. Once a negative charge goes away, it results in a positive net charge left behind. So every time an electron moves out of its spot, it leaves behind a positively charged hole. So you have positive charges here, and negative charges on the other side, and this gives rise to VC, capacitor voltage. So the movement of electrons between the source and the plates of the capacitor is what we call as the flow of electric current. Technically, current is not actually flowing through the capacitor, not physically. Physically, there are no electrons that are crossing the plates. Yet, we always refer to as capacitor current or current flowing through a capacitor. But technically, physically, it's not possible. Separated by an insulator, so electrons are not going through that insulator. Okay? Yes. Yes, so the process stops when the capacitor voltage VC equals the source voltage Vs. There's no more charge imbalance, and because there is no more charge imbalance, that process transfer stops. So if Vs is a DC source, mathematically, you tell me what happens. I equals C times dV over dt. So if V is a constant, a DC source, what happens to I? Just mathematically. It's zero. Derivative of a constant is zero, right? So mathematically, we can just say when the voltage across the capacitor reaches full charge, meaning VC is equal to Vs, current I or IC goes to zero because electrons are no longer flowing. If electrons are no longer flowing in the circuit, then it's equal to zero. Okay. And same thing for an inductor. In the inductor, we have current flowing through, and current flows through. We say inductor voltage V is equal to L di over dt. So if the current is constant, let's go back to that slide. This one, right here. What is the voltage sustained to a constant current? If the current is constant, it does not change, then the inductor behaves like a short circuit. The voltage across that inductor is equal to 0. Both ends of the inductor are at the exact same electric potential. So current flows through inductor. If you're applying a DC current, it takes some time for it to charge up. Once it reaches full charge, it behaves like a short circuit. And so V equals 0 if I is constant. At that point, we say that the inductor and capacitor have reached full charge. They are fully charged. Again, this is for DC. So you take a DC battery or a DC power source and you connect it to a capacitor or an inductor. It will receive the energy. Okay. Once it receives the energy, it reaches full charge, and that's it. Once it reaches full charge, voltage for inductor is equal to 0. It behaves like a short circuit. And you have to remember, inductor is nothing but a coil of wire. So wire itself, unless it has high resistance, which is not true, high quality inductors typically have resistance less than 5 ohms. So it behaves like a short circuit. Full charge. And then here the capacitor behaves. I goes to 0. V is constant. Reaches full charge. And what does the capacitor behave like? Anyone? If inductor behaves like a short circuit, and for a capacitor, if I equals to 0, open circuit. So similar behavior, but exactly the opposite. We use capacitors every day. You've been using it right now. Anytime you touch your devices, your fingers are forming a capacitance layer with your touchscreens. So these are all capacitive touchscreens. The capacitance of that screen changes, and it is sensed, well, there are multiple sensors in there, but it's sensed by the glass layer or the touchscreen layer. So anytime we touch with our fingers, capacitance changes, the change in capacitance is sensed, and it then tells you where the position is. Prior to capacitive touchscreens, we had resistive touchscreens, and those resistive touchscreens required like a stylus, so point stylus. And the reason we required the stylus is because they were resistive touchscreens. So anytime you touched it with a finger, you had to like press down. So the sharper the touch, the easier it was to change the resistance of that screen or the sensing layer. And so when the resistance of that screen changed, it would be registered or processed as the position of that touch would be processed, and you would have a touchscreen. So both resistive as well as capacitive touchscreens function in similar ways, but resistive touchscreens require a stylus to create like, a large amount of pressure. If you wanted to use your fingers, you had to like press down on it. Anyone ever use a screen like that? They are not as widely available nowadays anymore. So the earlier devices, like the Palm is a company that no longer exists, but Palm Pilot organizers, Palm organizers, personal digital assistants, they were all the rage just until a few decades ago, right around the time the BlackBerry went out. All right, so that's real life applications of resistors, capacitors, and inductors, all right? Okay, linear functions, definite integral. One final summation of these slides is that we have sources. Sources supply energy or I would say the other way around. Any device that supplies energy is a source. Any device that receives energy is a load. So these are all loads. These are all sources. We use switches to control our electric circuit. More often than not, we don't use them. We just illustrate that circuit is pre-built and the connection is already made. Then we have energy storage devices, inductors and capacitors. Inductors and capacitors can behave like a source if it does have stored energy. Okay, but it cannot supply this energy infinitely. Okay, there's a finite end to that supply. So a capacitor or an inductor can store energy and can supply energy, but that supply is not infinite. Okay, so it stores energy and then it releases back into the circuit. The time difference between storing and releasing could be as small as nanoseconds, microseconds, milliseconds. Depending on the size, it could be anything, right? There are also some things you have to care about, which is not the focus of 115. That's something that you will look at in 215. It's charging and discharging. Charging and discharging, meaning when the capacitor or inductor receives the energy, we say that they are being charged. When they release that energy or when they release the stored energy back into the circuit, we say that they are being discharged, right? The charging and discharging cannot happen in an instant. Thanos could have all the Infinity Stones in the world that he wants, but it's not gonna go with a snap of your fingers. It takes a finite amount of time. There are equations that govern, there are mathematical equations that are derived to describe the charging and discharging process. That takes place later, not in this course. All right, let's take a pause. Let me know if you have other questions. Yes. Yes. So the question being asked is what do we mean by load or consume? The answer is, and I think you answered the question itself, that yes, it does mean that they are receiving the power. So anything that supplies energy is a source. Anything that receives energy is a load. Capacitors and inductors do not have any energy of their own. So they must first receive the energy. They first behave like a load, and then they can behave like a source, but not constantly. They can only behave like a source for a small instant in time. So technically, they are not sources. The exception, I would say, are rechargeable batteries. If you charge your battery, then the battery is acting as a load because it is receiving the energy. When you remove the charger, now the battery is supplying energy to your device, hence it is now a source. So in the true sense of the meaning of those both words, rechargeable batteries can be described as both source as well as a load. Yes. Which one? Rechargeable batteries. The question being asked, is it a really, really slow capacitor? No, because it's not just parallel plates separated by an insulating material. A battery is something that is completely different. The batteries that we use are made out of it functions on the fundamental operating principles of electrochemistry. So there are chemicals inside batteries, and those chemicals interact. So electrochemical reactions are taking place. And the result of those reactions is that a voltage difference appears across its two terminals. Okay, We have 5 minutes left, so I want to begin the next slide. And then we talk about, well, we already did this, conversion of electrical energy into some other energy. And I think I've spoken about this too. Most electrical energy is converted into thermal energy, dissipated as heat. Some devices dissipate it as heat and light, which is our LEDs. Some devices convert light into electrical energy, which is solar cells. Anytime the energy is converted from, well, let's say electrical energy is converted into another form, or some other form of energy is converted into electrical energy, there are losses that occur. These losses, depending on how small or big they are, is defined as efficiency of the system, right? So if you have some amount of electrical energy going into a system, let's say 100 units of electrical energy, and the output is only 50, you'd say it's 50% efficient, right? Most devices, again, most devices are highly inefficient in that sense. Solar cells, by the way, are not very efficient. They are the best technology that we have. Over the last few decades, several researchers around the world have been trying to work with different materials, different kind of structures, different semiconductor designs, all in the name of trying to get its efficiency up. So approaching anywhere above 20 to 30% efficiency, that's the max of a solar cell. Yes. Absolutely. Question being asked is, if we use diode in a circuit, does it also lose energy? The answer is yes. If you have an experiment where you're applying a large amount of voltage or current to a diode, it will get hot. So, and if you go beyond its rating, it's going to blow up. So all devices get hot. Anyone ever see heat sinks on any electronic device, like desktops, especially desktops, right? Desktops have these big CPUs. Those CPUs have billions of transistors, billions with a B. And we'll talk about that in the next class, unit prefixes. And each one of these transistors is just dissipating like picowatts of energy, picowatts of heat. That is very, very small, insignificant. Picowatt is nothing, 10 raised to minus 15. But if you multiply the 10 raised to minus 15 into another 10 raised to minus 15, now the heat dissipation of billions of transistors in now tens of watts. Okay. And so all of those acting together, even though it's a tiny amount of heat being dissipated, all of them, the sheer quantity of those transistors is what makes it heat up. And so older times, laptops, even some laptops nowadays, you have like fans inside the laptop. That's to pull the heat away from the heat sink and, dissipate it into air away from the laptop. Okay, so you have heat sinks still in existence today. Your tablets also get hot. Mobile phones also get hot. There are some tiny heat sinks on there. Heat sink, as the name suggests, will sink the heat away from your microchip devices and dissipate it out into the atmosphere, away from the device. Okay. All right, so we'll end the class here today, and we'll pick up here again on Monday. There's quiz 1 on Monday. That quiz is just based on the lectures that we have done over this past week. So Monday, Wednesday, Friday, right? So I will post an announcement regarding the quiz. Later today, I will also post the homework. You'll have more than 1 week to get done with the homework. I'm trying to set a regular schedule. So I don't know if I want to go from like Friday to Friday, or I might go Saturday to Saturday, or maybe Friday to Sunday or something. I don't know. Maybe I'll ask the students on Monday once everyone is here. All right. So quiz on Monday. Again, there's no online option for the quizzes, so everybody better be in class. Otherwise, you're going to miss it. All right. Have a good weekend, and I will see you all on Monday. Yeah.
Program before. Do you know if there's like any shortcut to like go to the next page? That's what I